maybe I'll just start the formality. So yeah, thanks everyone for coming to the lecture 3 and 4 of Pierre. We're going to start in 1 second. Are there any announcements, Subhajit, that we need to make, or is everything's good? Okay, in that case, I'm going to hand it over to Pierre. So Pierre, over to you.
Okay, so thank you. Can you hear me? Hello, hello. Is that a yes?
Oh yeah, we can hear you. Yeah.
Okay. Great. So good afternoon. I see you all flocking in sandals. I wish I could do the same. Anyways, we have sun, which is not a trivial statement hereabouts. Okay, so this is going to be a double bill, and there is going to be a break in the middle, and I tried to not plan too much, to do too much, so that we, hopefully it will be digestible. Okay, so let me start by recapping some of the things that I said yesterday. Okay, so briefly, the setup was that we had a transient graph. So transient means transient for the random walk, which I denoted by x, so discrete time. So this is the random walk on G. Okay, and for simplicity, let's say it chooses its neighbors uniformly at random, though I will need a slight generalization of this a little bit later today. And then we had phi, which was the GFF on G. Okay, so this is a Gaussian random field indexed by the vertices, so you should really, I mean, you should do whatever you want, but I like to think of this as sort of a landscape that exists on top of the vertices of my graph. Okay, and so yesterday I proved the following theorem. Okay, so I showed that if you look at any, so K is any finite subset of your graph, the disconnection probability, so the probability that you do not have a connection in the level set above level minus anything. So maybe let me just recap, right? This means A connected to B above, say, A for any real number A is the event that you have a connection. So, path, nearest neighbor paths of vertices along which the field stays above this threshold. So it's a path in this excursion set. Okay, and what we proved is that this is bounded for any negative level by e to the minus a half a squared times the capacity of K. Okay, so if you just, this is still things we did yesterday. If you just take, K to be a single point, then you will immediately infer that actually you have percolation of these excursion sets above any negative level. So, there is a critical parameter AC, which, depends on your choice of graph. So this is, percolation threshold for these excursion sets. Okay, so the picture is, here's your real line. This is your, P or A as it's parameterized here. Somewhere there is an AC. And so because the level sets are decreasing, the supercritical regime sits here and the subcritical sits here. Okay, and so you get that this AC of G is actually non-negative. That's a direct implication of this theorem. And so let me just briefly say a word. Much more is actually known. This whole problem of disconnecting, this is a disconnection probability, right? So for k equals say 0, a distinguished vertex in your graph, this probability is bounded away from 1 for any a positive, and therefore you have percolation. Okay, and much more is known, so I want to briefly mention this because it's stuff that people have been working on quite a bit. So for instance, if you take G equals ZD, so D greater or equal to 3 for things to be transient, and you take, say, K, any compact subset, which is regular, so let me not venture into what regular means here. So, I mean, you can think of it as, for instance, being actually the whole box. That's already interesting. And if you look at the probability that it's blow up, so I'm going to write this as n times k, and you should think of this as this set here. Okay, so this plays the role of k in my theorem. So the probability that, say, this is disconnected from the boundary of a twice bigger box at level A. So this has actually a very precise asymptotic behavior as n tends to infinity. And actually, the behavior is, well, maybe let me write it like this, up to a constant which is explicit and depends only on D, A minus A star squared over 2 times the capacity of A. So this is something which at this level of generality has been proven by Nitschner. And so here there's been lots of stuff going on. So the players here are sort of the names I'm writing down there. So Snitman, Nitschner, and Chiarini mostly. Okay, so okay, this is the tip of another iceberg, but I just want to mention this in passing. And so, in particular, if you look at this theorem, so it's a little bit more general because it works for any set k, but actually, so you see this dk in the capacity of k is actually correct to leading order for many sets. And so the a squared is actually not quite correct. You see that there is the truth is you have to put a star here. And so you know that, sorry, a star is AC, my bad, it's the critical parameter. And you know that it's non-negative, and in fact, in many cases, so in particular on ZD, so maybe I can squeeze that here.
Sorry, just to clarify, so it's capacity of A is capacity of K, right? And just to check, A is less AC, so it's in the supercritical, or?
Yeah, thank you. Yeah, so this is capacity of K, and this is the RD capacity, and this is in the supercritical. Sorry, and there is, I guess, you should normalize by, sorry, so maybe okay, I think now I have everything I need. Yeah, sorry, it's still early, so I have to heat up. Okay, so actually you can prove that this critical parameter is strictly positive on ZD. This is something we showed with Alex and Alexei some time ago. And so so the result of this theorem is not completely sharp, but of course to get these precise asymptotics that I wrote at the bottom, you need to work arguably infinitely harder. So yeah, but just to mention that we actually know what the correct behavior is.
What do you mean by RD capacity of K?
So K is a subset of 0, 1 to the power D, and that's just the usual Brownian capacity. So with respect to the, you can write it, for instance, in terms of a variational principle involving the, the Dirichlet energy on RD.
Okay.
Yeah. If you don't like the RD capacity, then you can stay with the capacity on your graph, the one which I defined, and you replace k by nk, and you remove the n to the 2 minus d that sits in front, and that's also correct. It's just that asymptotically it behaves like this rescaled capacity of the compact set in RD. Okay, so I want to briefly take 10 minutes and say a little bit more about why this capacity bound comes up, because the point of me mentioning these results down here is that actually this is sharp for these disconnection problems if you forget about the dependence on A. And so if you remember in the proof yesterday, I told you we were going to build this little observable that's some average of the field values in K, and the right choice is actually to normalize them according to the equilibrium measure. But I said you could also do a more naive average, even though then this is the optimal choice. And so I want to quickly touch on this optimal choice because it's actually important. So let me give you another example which is simpler and where this capacity comes up as being, in a sense, optimal. Okay, so here is a little lemma which is actually useful. So again, K is a finite subset, and A is positive. So you can look at something very simple like the probability that phi is, say, bigger than A for any point X that belongs to the set K. And I claim that this is bounded by the same quantity. So 1/2 A squared cap K. Okay, so why is this, and why does the capacity pop up? Well, so here is a proof. It's a simple proof. Just take nu to be any probability measure supported on K, and then of course the left-hand side, the probability that you're above A for any point in K is bounded by the probability that if you average with respect to nu, which yesterday I wrote in this way, so maybe I remind you, nu phi is just the sum over X, nu X by X, and you can lose this. Nu has a finite support, be it what it may. So if you average them, then of course this also has to be bigger than A. And the upshot of having this is now that this new bracket phi is just a single scalar Gaussian random variable, and so this is bounded by usual Gaussian tail estimate. So you could put stuff here in front, but let me not go there. So you get e to the minus A squared over 2 times the variance of this random variable. Okay, and so if you compute the variance, so let's do that. We did something close to this yesterday. So everything is centered, right? So this is just the second moment. Okay, and so you get this kind of what you might call the energy of this measure nu. So I'm just using that I have a Gaussian free field and I'm unpacking the square. Okay, so this is, let me give this a name. This is E of nu nu. Okay, so I can replace this thing here by E of nu nu. So this is true for any nu. And of course, nu here can be anything you want. So to get the best upper bound possible, you want to take the infimum of this bound over all probability measures nu supported on your set. Okay, so the question is which nu achieves the optimum, and so here is a little side calculation, so maybe I can write this here. So in fact, the infimum over this quantity as nu ranges over probabilities on K is exactly 1 over the capacity. And that's why the capacity comes up. Okay, and the proof of the claim is is actually quite simple. So if you plug in nu equals the normalized equilibrium measure, which is a particular probability measure supported on K, then you get equality. And this calculation, we already did it yesterday. This was this bit here. And basically, if you remember what happens if you, so here, this is exactly the energy of EA bar. So here it was A, not K. And maybe I should have made up my mind. Anyways, and then you just use that, when you do one of the sums, then, this integral or this sum of G against EA gives you the probability to hit K, but X here is a point which is also in K, so this probability is just 1, and then this simplifies to 1 over the capacity. So you have actually a measure which achieves the quantity on the right-hand side. And so more generally, if you have a different measure, then you can just write, so this energy form is bilinear, so, and all the sums are finite here, so there's really no issue at all. So I can write this as the equilibrium measure plus the difference, and then there's also going to be cross terms, so maybe 2 of them of this form. Okay, so let's go through these terms individually. So okay, we know that this guy gives me capacity to the power -1. So here I claim that this term is 0, and the reason for that is that so actually this was nu minus. If you look at each of the, I mean, you can split this up into a difference of 2 terms, and you see, even if you have nu here and only EK bar over here, you can still perform the sum over Y. You're going to get, 1 over the capacity, and when you sum over nu, then this is still a probability measure that sums up to 1. So even if one of the 2 arguments is not the equilibrium measure, but a general nu instead, you still get 1 over the capacity. So here you're going to get 1 over the capacity minus 1 over the capacity, so you get 0. And finally, this last term here is non-negative. And so, so here you have to be a little bit careful because, this difference now is a sign quantity. So this is not completely obvious, but actually, this is positive definite. So indeed, it's non-negative. And so you see for any other measure, you can only increase this energy, and that's how you prove this claim. Okay, and now you feed this claim into the above estimate, and so the infimum is actually achieved by choosing nu equals the equilibrium measure. Okay, so we have this bound, and you see how the capacity appears because you are somehow optimizing. Okay, so I just want to make 2 comments about this bound. So you might wonder, well, how sharp is it? So actually, it's often not far from being sharp. And let me give you an example of this. So I'll just give a simple example. You can take, for instance, A equals 1 and K to be a box of radius n, and let me focus on G equal to ZD here. So then this is sort of a classical problem which is called the hard wall condition, and this has been studied by people like Bolthausen, Deutschel, and also Zaituni. There's, I mean, again, it's the tip of an iceberg, and there's actually also recent activity by other people. So here, it turns out that you can again compute a relatively precise asymptotic for this probability, and it turns out that so remember, if you have k equals n, then the capacity gives you n to the d minus 2, and the correct answer is actually that the dk is n to the d minus 2 times log n. So you're missing a log n in the exponent, but log n is subpolynomial, so it's you're not actually missing much. Okay, and so in general, I mean, the upper bound you get tends to be not too far from the truth, and so I mention this because it also has other ramifications. So I showed you how to prove that that AC here is greater or equal to 0. So you have to look at this picture now. So this means you have a non-trivial supercritical regime. You might also wonder how to show that AC is finite in order to be sure that you actually have a non-trivial phase transition. And well, you see that this question is not so easy to answer, because if you believe me for a second that this lemma tends to be, the bound from this lemma tends to be not too far from the truth, then actually it's it's quite possible. I mean, it's true in many cases in practice that the capacity of K can be, and is often, I should maybe say, sublinear in the size of K. And now, why do I mention this? Well, because if you follow, for instance, the argument in Bernoulli percolation. So now we're talking, how do you prove that PC, is positive, so that when P is close to 0, you don't percolate. So very simple argument is just to say you're on ZD, for instance. Well, you take a union bound over all the paths of length n. So this grows exponentially in n, like say 2d to the power n. And then the probability for any such path to be open is p to the power n. So if you take p to be less than 1 over 2d or something like that, then this probability decays to 0. Okay, and here if you try to do something similar, so again, you're going to, if you do a naive union bound over path, then that, union bound grows exponentially in the length of the path, but the probability to be, everywhere open along this path is exactly the probability that phi x is bigger than a. So you think of k as being the range of this path and a as being very, very large. And this may not actually compete with this capacity. So for instance, if the path is winding around and forms a box, then you will get something which is a small polynomial. And even if you think of the path as being sort of extended, of its diameter to be of order n, even then the capacity can be sublinear. For instance, in 3D, the capacity of a line of length n is actually n over log n. And so this is why to prove this non-trivial subcritical regime, you actually need to do something more clever than this kind of bound, and that's where you need sort of multi-scale analysis. Okay, and I'm not going to go into the details of this, but if I have had more time, maybe I would. But this is essentially why you need that. Okay. So I hope I convinced you a little bit that the capacity appears as a sort of optimizer. And so now we know, I'll write it again, coming back to my disconnection probability, that, so this is what we proved yesterday. And the argument I gave you, which is, modeled after an argument of Brickmont, Leibowitz, and Mass, is not really constructive. I showed you that at negative levels, somehow, if you do a little test function around this set K, then it fields the harmonic shift from the boundary at negative levels. But I didn't really construct. I mean, this statement is saying that you percolate at negative levels, so you have an infinite cluster. Okay, so the proof was non-constructive. And so a fair question that you may have is, so what is actually percolating? Okay, and so I'm going to answer this question for you, and basically in answering this, I'm going to give you another proof of this statement I wrote to you up there, which is actually constructive. So, okay, the short answer, so maybe I draw a picture. Here's my set K. The short answer is that it's percolating because you can actually draw a random walk trajectory on which the field is greater or equal to minus A. Now, so of course, if that were true, then you could say, well, okay, now I understand why things are percolating, because this random walk trajectory is transient, so it goes off to infinity. So in particular, its range is an unbounded connected component. Now, this is not a very good answer. It's sort of a level 0 answer. And the reason why it's not a very good answer is because, as you know, for sort of ergodicity reasons, for instance, if your graph is transitive, then, this infinite cluster is its law is supposed to be invariant under translations. And the problem with random walks is, I mean, I love random walks. I'm their biggest fan. But somehow the problem with random walks is that you need to start them somewhere. And here, this starting point, it sort of breaks the translation invariance of the problem. So somehow you would like to have something like a random walk that doesn't have a starting point. So what do you do if you have a random walk and you want to not have a starting point? Well, you make it into a loop. And that's essentially deep down the reason why all these loop soups come up in these models. Okay, so now you want to make it into a loop, and you want to still make it percolating, and so this thing has a name. It's called interlacements. And what this is, so I'm not going to define them to you exactly, but what these things are is you should think of them as a loop soup, if you know what that is. That's in some sense coming from infinity. And maybe a good picture to keep in mind is to still think of a random walk, but think of you going along with the random walk, and you, instead of looking at it like this globally, you look at it from a typical point on the trajectory. So of course, as time evolves and it becomes larger, then you will have some sort of infinite past and infinite future around you. And I mean, this actually stationarizes. Okay, so so these interlacements, they form this kind of Poisson soup of trajectories. So think of these things as being loops that close at infinity. And so you don't need to know much about them. So these interlacements, they correspond to a sort of stationarized law of my random walk. So this is, maybe in quotation marks. And they come with an intensity U. And basically U tells you how many, it's the intensity factor in the intensity measures. It tells you how many random walks you throw down. And you don't need to know much about random walks except the following fact. So the number of trajectories that hit the set K is, well, I told you there are Poisson number of them. So this is actually a Poisson random variable, and its parameter is U times the capacity of K. Okay, and so now there is sort of a relatively deep theorem, and so this, goes back to what are called Raynight theorems, but in the version I'm stating it here, it's actually an observation due to Titus Lupu. And the observation is the following. So if you define IU to be the union of the ranges of all the trajectories, so this is all this yellow stuff here. Sorry. So actually, you can even prove that they form a connected set. So somehow, somewhere, these guys will actually meet. Okay, so this is IU. Then the theorem is that so there exists a coupling of this, random yellow spaghettis and a Gaussian free field with the property that the free field is greater than minus A on the range of IU if you choose U to be A squared over 2. So once you have access to this theorem, you have an alternative proof of the statement that I wrote up there, because, of course, what this theorem implies is that if, so maybe I'll do it on the next page. So the theorem implies that if this yellow soup at my well-chosen parameter happens to intersect my set K, well, then I've lost. Then I cannot have this connection. I have a connection to infinity. So then K is actually connected by the yellow set, and hence also in my excursion set for my Gaussian free field to infinity. And that's because this yellow set is built of bi-infinite random walks that are percolating. And so so if you read this reversely, so if you want the probability that K is not connected to infinity, well, then you better not have any yellow stuff that hits your set K. And so I told you the number of yellow trajectories that hit the set K is a Poisson random variable with this intensity parameter U times capacity of K, and U is A squared over 2. So you want really that a Poisson random variable with parameter U capacity of K, U here is A squared over 2, be 0, no yellow stuff. And well, Poisson being 0 is either the minus the parameter, so it's either minus A squared over 2 times the capacity. Okay, so this is just another proof of this statement, but this one is constructive because I'm actually telling you what part of the infinite cluster is. And in fact, you can even refine this statement and understand more precisely what the infinite cluster is. So if you refine this coupling, which you can do, I'm not going to discuss it here. You can even refine it in such a way that this thing here doesn't really become an inequality anymore. So I'm not going to discuss this here, but there is an even more precise understanding. Okay, so any questions about what I just said?
Yes, can I ask? For the infinite cluster in the supercritical phase, I guess it's not so easy to get a finite energy for the model. So is the infinite cluster unique, or is it more complicated?
Yeah, so it is unique, and you do have finite energy. So it depends what you mean by finite energy. What I mean is just that, the probability that, say, a point is open, so which would be this, or given you condition on everything around it. So maybe you want to condition on the phi, or maybe even just the configurations. That's all you need. So this is non-degenerate in the sense that it's positive. So it's not bounded away from zero uniformly. I mean, for instance, if you condition on everything outside of your point inside of a box of size L, then the bound you're going to get here is going to be a function that actually decays polynomially in L when L tends to infinity. But you do always have some residue randomness sitting here. And so one way that you can view this is, you can decompose your Gaussian free field over scales. And when you do that, there is always residual randomness at scale 1, and that randomness doesn't see anything that happens around you. And so, long story short, you can actually, perform the Burton-Keane argument and use it to prove that that you have a unique infinite cluster.
I have one question. So is this classical Raynight, and what is the connection? I don't see.
Yeah, it's not classical Raynight. It's maybe something you might want to call generalized Raynight. And so the way you should think of this is that you can relate the okay, I can write it, then maybe it will become more clear. So the theorem is roughly that if you take a free field squared and you add to it the occupation time, which I haven't defined, of these yellow trajectories, so they all come with their local time, and you can define a field LXU, which is just how much time is spent at X by any of the trajectories in my soup, then you have a statement of the following form. So these two things are independent. And so this is equal, okay, maybe I need to put a 1/2 here. This is equal to a shifted Gaussian free field in law. So this is the sort of Raynight theorem over which you improve to get a coupling like this. And this, probably starts to look, I mean, if you replace things by a Brownian motion, it starts to look perhaps more like the classical one-dimensional version. If you want to get back the classical theorems, then you should think of your Gaussian free field that appears here sort of maybe on a one-dimensional segment with zero boundary condition, and then this Gaussian free field measure is just a product measure in the increment. So it will converge to something which is like a Brownian bridge, and this is how you can this is the sense in which this generalizes classical Raynight theorem. So this is where this is coming from. Yeah. Any other questions?
Just to clarify, your IU reads as equal to union of ranges of all trajectories?
Yeah, so IU is this yellow stuff.
Okay.
So you throw down a Poisson point process of loops, but they are loops that come from infinity. So they go through a point at infinity. So the way you should really think of this is that there is a natural measure on bi-infinite trajectories if you kind of forget about their time parametrization, which is implicit when you talk about loops. And So you have a natural object, which is kind of this by infinite random walk, but it's arriving from infinity, which means that, you know, you don't need to, I mean, you see the naive way to do things would be maybe if you need to start it somewhere, then you pick a large box, you pick a point uniformly in this box, and then you just launch two trajectories from that point. But that's not something which is, you know, stationary with respect to the shifts in time on, you know, in Z. But there is a way to stationarize things, and this is exactly this Poisson process. And so when you sample it, you are basically sampling a random number of these yellow these yellow loops, these yellow infinitely big loops, and the number of such loops that hit a certain set k, well, it's a Poisson number because it's a Poisson point process, but the intensity is of this number of yellow loops is exactly U times the capacity. So this comes from the way the intensity measure looks, but there is only one choice for this intensity measure. And if you are maybe familiar with the more classical Brownian loop soup, then you can actually also construct these interlacements by looking at a regular loop soup. Then you look maybe at the loops that intersect the boundary of a large box, and if you suitably rescale them so that you see something in the limit when you take the box size to infinity, then, you know, they will converge towards this interlacement point process.
Any questions in the Zoom? No. So everything's good here.
So this may actually be a good point to make a break. Is that agreeable?
Yeah,
I mean,
that's
I
agreeable.
can also continue, but then it's gonna cut a little bit in the middle. So
No, that's fine. Do you still want to break to 3:15 Indian time, or do you want to start?
no, I mean 10 minutes is fine. Yeah.
Yeah. So okay, we do a 10-minute break then, and we start again at at roughly like 3:10. And maybe just for people, the slides of the first two talks are on the webpage now.